Next example of vector space. Let V is equal to M2 by 2R. So this is the notation for set of all 2 by 2 matrices with real entries. So order of the matrix is 2 by 2, and the entries, that is the elements of that matrix, are real numbers. Okay, so this is the set of all 2 by 2 matrices with real entries. And for A is equal to the matrix A1 B1 C1 D1, and B is equal to A2 B2 C2 D2, we define A plus B as that is A1 B1 C1 D1 plus A2 B2 C2 D2 is equal to A1 plus A2 B1 plus B2 C1 plus C2 D1 plus D2. Is again the 2 by 2 matrix. Addition of two matrices of order 2 is again the matrix of order 2, and it is your usual addition of two matrix. We know the addition, how we can take the addition of two matrix, that is the addition of the corresponding entries. So, and the scalar multiplication, suppose K is scalar, K is number, K is the element of R, and then K into A means K into A1 B1 C1 D1 is K A1 K B1 K C1 K D1. So this is the scalar multiplication, is again usual scalar multiplication of number and matrix. Okay, so under these two operations, this M2 by 2R is a vector space. So this V is equal to M2 by 2R is a vector space with respect to these two operations. So we can write its proof, that is the 10 properties. The addition of two matrices is again is the matrix of order 2 by 2, that is closed for addition, that is C1 property is satisfied, C2 property, one scalar and one matrix, its multiplication is again 2 by 2 matrix of with real entries, means K into A belongs to M2 by 2R for all K and for all A, that is the M2 by 2R is closed for scalar multiplication. Like that we can prove the property number A1, A2, A3, A4, M1, M2, M3, M4 very obviously. And therefore under these two operations, this set M2 by 2R is a vector space. So the proof, as far as the exam concerned, the proof of this example is not important. Just remember how we can define the addition, how we can define the scalar multiplication. Usual scalar multiplication, usual scalar addition of two matrices is the operation. So this set M2 by 2R is a vector space. So what is the zero of this vector space? This zero matrix of order 2 by 2, 0, 0, 0, 0. The zero matrix is the zero of this M2 by 2R. And what is the zero of R2? 0 bar as a 0, 0 order pair. What is the zero of R3? 3 tuple 0, 0, 0. This is the 0 bar. In Rn is what? N tuple of all entries are 0. So this is these are the zeros of the vector space Rn or R2 or M2 by 2R. So if we take the instead of this M2 by 2R as M cross N, R means the set of all M by N matrices with real entries. M 2 by 2 instead of 2 by 2, take M by N matrices, set of all M by N matrices with real entries. This is the notation M, capital M cross N, R. The set of all M by N matrices with real entries. Then this set M, this vector space M by N R is a vector space with respect to the usual addition of matrices and usual scalar multiplication of matrices. That is one number scalar and one matrix. So similar to M2 by 2R, this is the vector space. Then the next example, V is equal to F, capital F in bracket, square bracket AB means closed set AB R. And what is this notation? This is the notation for set of all real valued functions defined on a closed interval AB. Set of all real valued functions. That is, this V is what? Is the set of all functions. That is, it is the set of functions. This M2 by 2R or M by N R is what? Is a set of matrix. This is the vector space of matrix. Like that, this in the example number 6, V is a vector space of functions. These are the functions, real valued functions, that is functions from closed interval a b to r, and for f and g belongs to v, define, that is the addition of two functions is defined like this: f plus gx is equal to fx plus gx for all x belongs to a b, closed interval a b. And the scalar multiplication is defined like this: k of x is equal to k f of x for any scalar k, and x belongs to closed interval a b. Then this is again the usual definition of addition of two functions. This is the usual definition of multiplication, scalar multiplication in of functions. Okay, k f x is equal to k f x is equal to k of fx. So under these two operations, this v, the set of functions, is a vector space. So we can also prove the give the example as solution of this example as the 10 properties. Then next is v is equal to Pn, the set of all polynomials of degree less than or equal to n. It is not the set of all polynomials of degree exactly equal to n. It is the set of all polynomials of degree less than or equal to n with real vector, real coefficients. That is what is Pn. Pn is the set of these types of polynomials: a naught plus a1x plus a2x square plus dash an x raised to n. That is, this is the polynomial, and this a naught, a1, a2, n belongs to R, means these coefficients are real numbers. So this is the set of all polynomials of degree less than or equal to n. This is not the set of polynomials of degree n. It is the set of all polynomials of degree less than or equal to n. If instead of this, if we take the set of all polynomials of degree equal to n, then it may or may not be vector space, because the addition of two polynomials of degree n, exactly n, is not necessarily the polynomial of degree exactly n. In sometimes the coefficient of x raised to n in the two polynomials by taking addition may be equal to 0. That is, addition of two polynomials of degree n may or may not be a polynomial of degree n. It is the polynomial of degree less than or equal to n. The addition of polynomials of degree equal to n is a polynomial of degree less than or equal to n, because by taking the addition, while taking the addition of two polynomials, the coefficient of x raised to n may be equal to 0. That's why this is the Pn is the set of all polynomials of degree less than or equal to n. So this word is important: less than or equal to n with real coefficient. That is, this is the set, and set of all polynomials. And for P1 and P2 as this: P1 as a naught plus a1x plus a2x square plus an xn, and P2, or write px and qx instead of this P1 and P2. Write notation P and Q, or P in bracket x, Q in bracket x, b naught b1x plus b2x square plus bn x raised to n belongs to V or Pn. These are the two elements. Define their addition P1 plus P2 at the addition of these two elements as a naught plus a naught plus b naught plus a1 plus b1x plus dash an plus bn x raised to n. That is, this is the addition of these two polynomials. That is your usual addition. The addition of constant terms, addition of the coefficient of x, addition of coefficient of x square. In this way, addition of coefficient of x raised to n. So this is the usual addition of two polynomials. And this k as a scalar, suppose k is a scalar, then kp1 or kpx is k, and a naught plus a1x plus an x raised to n defined as k a naught plus k a1x plus k a2x square. In this way, k a n x raised to n. So this is again the usual multiplication of one number and one polynomial. And so under these two operations, addition and scalar multiplication, this Pn is a vector space with respect to these two operations, addition and scalar multiplication. So instead of n, if you take n value of n is 2, then what is P2? P2 is the set of all polynomials of degree less than or equal to 2 with real coefficient. That is, what is P2? V is equal to P2 is equal to a naught plus a1x plus a2x square, where a naught, a1, a2 are the real numbers, belongs to R. And this set P2 is under these two operations. Suppose Px is a naught plus a1x plus a2x square, Qx is b naught plus b1x plus b2x square, Instead of this P1 and P2, here the notation are Px and Qx belongs to P2, be two elements. Then the addition is what? A0 plus A1x plus A2x squared, that is Px plus Qx is equal to A0 plus B0 plus A1 plus B1x plus A2 plus B2x squared. So this is what? The addition of two polynomials of degree 2 is again the polynomial of degree 2 or less than or equal to 2. Suppose if it is the value of A2 plus B2 is 0, then it is a polynomial of degree 1. But what is the addition of the polynomials of degree 2? It is again a polynomial of degree less than or equal to 2. That is Px plus Qx is again the element of P2. If Px and Qx are the element of P2, then Px plus Qx is again the element of P2, because Px plus Qx is what? Is a polynomial of degree less than or equal to n with real coefficients. And so this P2 is closed for addition. For P2, C1 property closure assume number 1 satisfied for P2. And what is Kpx? Is Ka0 plus A1x plus A2x squared. Then Ka0 plus Ka1x plus Ka2x squared. That is multiplied by K to each real number, real coefficient. Okay. So this is again usual scalar multiplication or usual multiplication of one number and one polynomial. And under these two operations, P2 is a vector space. So in this P2, the 0 vector is what? In Pn, 0 vector is what? 0 plus 0x plus 0x squared plus 0x raised to n. This is the 0 vector or 0 polynomial. And this is the 0 vector of P2 is what? 0 plus 0x plus 0x squared. This is the 0 bar or 0 vector of this P2. So under these two operations, P2 is a vector space. Then these are the some examples of vector spaces. These are 8 examples of vector spaces. Now we have to give the examples which are not vector spaces. So when the set is not vector space, if the set does not satisfy any one property out of the 10 properties of the vector space, then that set is not vector space. So we given the first example is let V is equal to 2 by 2R. That is again the set of all 2 by 2 matrices with real entries. A is equal to this set, this matrix. B is equal to this matrix. Then addition is defined like this: A plus B, A plus E, B plus F, C plus G, D plus H. That is usual addition. And the scalar multiplication is defined like this: Ka is equal to the matrix Ka 0 0 Kd. So this is the given definition of scalar multiplication. That is, this is not usual scalar multiplication, and we have to determine whether this set is a vector space with respect to these two operations. Justify your answer. So under these two operations, this set is not vector space. The addition, the operation addition is defined as a usual addition, and so out of the 10 properties, the property number C1 and the property A1, A2, the properties A1, A2, A3, A4, these 5 properties depend on the definition of addition. And in this example, the definition of addition of two vectors from this V is usual addition, means these properties are not dissatisfied for this set. That is the property number C1 and the properties A1, A2, A3, A4 are satisfied for V, because the addition is the usual addition in this example. But the scalar multiplication is not your usual scalar multiplication, and that's why out of the property of 5 properties of the multiplication, that is C2 is the property depend on the definition of scalar multiplication, and the properties M1, M2, M3, M4, out of these 5 properties, any one property may be dissatisfied or fails for this example. It is possible, because the definition of scalar multiplication is different than the usual scalar multiplication. And here the answer of this problem, that suppose A as the matrix 2 by 2 matrix 2, 3, 1, 4. Obviously this is one of the element of M2 by 2R, and then 1 into A is 1 into 2, 3, 1, 4. And what is its multiplication? Is 1 into 2, 0, 0, by using this definition. We don't use the definition of your usual scalar multiplication in matrix. That is the, we use the multiplication, how we can operate this multiplication like this. What is the given in the example? So 1 into 2 into 3 into 1 into 4 is what? 1 into 2, 0. These entries are fixed, 0, 0, 1 into 4. So this is by using definition of scalar multiplication given in example. Don't use the definition of usual scalar multiplication, because there the multiplication is given is not usual scalar multiplication. We have to use the multiplication definition of scalar multiplication given in example. So the example, in the example, this is the multiplication, scalar multiplication. So use that example, that definition. So we have this, and we have the answer 2004, and this is not equal to a. What is a? Is 2314. This is not 2314. This is 2004, and this is not a. So 1 into a is not equal to a in this example. That means the property M4 fails for this example, and therefore this vector V M2 by 2R is not vector space under the given two operations, under the given, with respect to the given two operations. So the set is same, that is M2 by 2R, but the operation, definition of operations are changed, and that's why the set is not vector space. So in order to, the set is vector space, the set is, just the set is not important, the two operations are also important. If we take the set as same, that M2 by 2R, we know that M2 by 2R is a vector space with respect to usual addition of two matrix and usual scalar multiplication. But the same set is not a vector space under the another two operations. These operations are given here in this example. So when the set is a vector space, if the set and with the two operations satisfies the 10 property. So in order to, the set is vector space, the set is responsible as well as the two operations are also responsible. But in order to, set is not vector space, again the set as well as the two operations are important, are responsible. Just not the set responsible for the set is not vector space. The two operations are also responsible to, in order to, the set is not vector space. So the set is important as well as the operations are also important in order to the set is vector space or set is not vector space. So here the set M2 by 2, we know that the set M2 by 2R is a vector space. But when the set is vector space, the set is vector space under the two usual addition and usual scalar multiplication. But if the definitions, here the definition of scalar multiplication is not your usual scalar multiplication. So the set is not only responsible in order to the set vector space or not vector space, the two operations are also responsible. So here the property number M4 fails. So we can also give the example or answer of this example, that take A as A, B, C, D, and then write that 1 into A is as A, B, C, D, that it is A, 0, 0, C, D, and then A, 0, 0, D, and it is not equal to A. So instead of this general example, we can give the particular example. It's called counter example. This counter example is justify that this M4 fails for the set vector space, and therefore V is not vector space under the given two operations. Okay, so how we can show the set is vector space? We can write the 10 properties. For example, this, how can write the answer of vector space? So if you have to show the set is vector space, then we have to write the 10 axioms, all 10, proof of all 10 axioms. But how we can show the set is not vector space? Just give the example, give the property which tells for that set. Suppose for set, we have the 5 properties are dissatisfied for set. Then give any one out of that 5 dissatisfied property. So how we can show the give the solution of the example that in which the set is not vector space? give any one property which fails for that set. Don't write the property that are satisfied for the set. Obviously, for this set, this for example, for this set, example number 1, the 5 properties of addition depend on the definition of addition, that is C1, A1, A2, A3, A4 are satisfied for this. So don't write that properties, the properties satisfied for the set. Just write that property which dissatisfied for the set, which fails for that example. So just write this answer of this example like this. Give the counter example. So counter example is the very best method to uh, give the example of examples of like set is not vector space. So if the set is not vector space, as far as possible, give the counter example. Instead of general example, give the counter example, particular example. Take A as this. Instead of take A, B, C, D, the matrix of order 2 by 2, take A as 2, 3, 1, 4. Or take any another element. Uh, this is not necessary that take A as 2, 3, 1, 4. We can also take A as 2 as A as minus 2, 4, 5, 1 half. Okay. Take any real matrix. Any 2 by 2 order matrix with real entries. Okay. And just show that 1A is not equal. But with, and therefore V is not vector space. So in some examples, uh, the property number here M4 fails. In some example, another property fails. So just give the example of that property which fails for that. So we will discuss in the next lecture all the examples in which the set is not vector space. So just give the counter example. Okay, that is the out of the 10 property, one property, at least one property fails for the set, then the set is not vector space. So just pick up that property which does not satisfy for that set and give the counter example of that set. Okay, that property. So we'll discuss the remaining examples of vector space. Actually, that the sets not vector space in the next lecture. So we'll see the remaining example in the next lecture.